Hi students, this is going to be a video narrating the PowerPoint for chapter 11, sections 4, 5, and 7. And most of this video is going to be on a topic called colligative properties of solutions. And those are properties that depend on the number of solute particles that are present, but not on what they are. So if you have a solution that has all the same solution, maybe 1 liter of solution, and one of them has 1 mole of sugar, another one has 1 mole of sodium ion, another one has 1 mole of something else, urea, all would have the same colligative property because it only depends on the number, 1 mole of the solute present, not on what they are. So those are all different molecules or ions, and so they would all have the same colligative properties because you're just counting how many particles there are, and you're not worried about what they are. So different properties that are solutions that are colligative are vapor pressure lowering, boiling point elevation, melting point depression, or usually called freezing point depression, and osmotic pressure. We're not going to go over osmotic pressure this semester, although I have a few slides at the end of this presentation for you to take a look at. So a little review, we're going to talk about vapor pressure lowering first. So vapor pressure is the partial pressure of the molecules that have escaped from the liquid into the gas phase. So right now we're not talking about a solution yet. That picture up there, this is just what will be the solvent. Let's say it's water. And its vapor pressure is the pressure of its gas molecules, so the water molecules that have escaped into the above the liquid. So then if you add a solute to your solution, let's say you're putting some sugar into some water, the vapor pressure will be lower than it was originally up here. So you have lowered the vapor pressure by putting that solute, by dissolving that solute in there. First of all, let's look at a little thing here. It says a non-volatile solute. That means a solute that does not have any of its own vapor pressure. So it's a solute that does not tend to evaporate. And that would be something like sugar, for example, that doesn't evaporate. Salt doesn't evaporate. So that's what the case we're talking about here, a non-volatile solute. If you had a volatile solute, something that does evaporate and has its own vapor pressure, then these things get a little more complicated. It doesn't follow what we're talking about now, and that's not for this level, of course. Okay, so think of it this way. You have some water, you put some sugar in it, you put some salt in it, you dissolve something like that in it, the vapor pressure is now less. Now, if you remember before, vapor pressure affected things like boiling, right? So this is definitely going to affect that kind of thing, and we'll talk about that in a minute. It happens because of a couple of things, because of the interaction between the solute and the solvent, that they're attracted to each other. So it's now not going to pop off as easily, the solvent into the vapor phase, but also because of the surface effect, because you see that these molecules here of the solute that you've introduced are at the surface in part, also down here, but also at the surface. And if they're at the surface, there's less area or place for this solvent molecule to get past it and get into the air. So it lowers, the bottom line is it lowers the vapor pressure. The equation that governs this is called Raoult's law, and we're really not going to do any calculations with this. I'm not going to quiz you on that. If there's any in the homework, you can just kind of do them just to get the idea of how it works, but I'm not going to give you these to do as a quiz question. So what it tells us is A is the solvent in this equation, and this is PA is the vapor pressure of the solvent above the solution. So this is the new vapor pressure after you've put something into the solution. P naught here is going to be the original vapor pressure, and XA is the mole fraction. So P naught here, this was the vapor pressure of your solvent all by itself. So let's say we're talking about a sugar water solution. This would be the vapor pressure of just water. And this is going to be the mole fraction of the water, okay? So not the mole fraction of the sugar, but the mole fraction of water. So this is all, A is all the solvent. And then this is the new vapor pressure. So since this is a fraction, it's going to lower this number. And so we have a new number here. This law works for ideal solutions. I'm not going to go into all the idea of what an ideal solution is. Sort of like there's an ideal gas, there's an ideal solution as well. So it doesn't work for all cases, but most real solutions will follow this as long as they have a non-volatile solute in them. Okay, so the next thing we're going to look at is boiling point elevation and freezing point or melting point depression. And so what happens is that when you have these solute-solvent interactions in the solution, they also cause the solutions to have higher boiling points and lower freezing points in the pure solvent. This is also related to the change in the vapor pressure. This is a little complicated here on this graph, but this is our phase diagram, and the darker line here, this is the original phase diagram for the liquid or the solute, I'm sorry, the solvent, I should say. So the solvent has a phase diagram. So imagine this is water or alcohol or something. Here's its phase diagram. When you dissolve something in it, now the line here moves a little bit to the left. This was the solid liquid transition line. So this is the freezing point depression. So now this one here, this sort of brighter blue line, this is the new freezing point line. And over here, this is our new boiling point line because this is the liquid gas transition. So you see that this number here, we're shifted over to the right. So for example, at 1 atmosphere, here was the original temperature that the solvent boiled at, and now it's boiling at a higher temperature. Okay? So we've increased the temperature of the boiling and we've decreased the temperature that it froze at. And we're going to be able to calculate this. So here's the equations for calculations for that. Here's the change in temperature of boiling. So how much the boiling point goes up, not the new boiling point itself, but how much it goes up is equal to a constant called the boiling constant, Kb, times the molality of the solution. So we learned how to calculate molality in the first video. And in this case, this is how much the freezing point goes down. It's a different constant, freezing point constant, times the molality of the solution. So in both equations, the change in temperature doesn't depend on what the solute is, but how many particles are dissolved, because molality tells you how many moles of your solute were dissolved. So there's nothing in here, and this Kf and this Kb, they depend on the solvent only, not on the solute. So whatever you dissolve, let's say in water, you use the same Kb or Kf. So that's why it's a colligative property. It only depends on how much solute is there, not what it is. So here's our equation again, and over here, this is table 11.5 from your book, and it says molal boiling point elevation constants and freezing point depression constants, Kf for several solvents. So I've circled the boiling one here because that's what we're going to look at. And these are just a bunch of solvents. They decided to list water, carbon tetrachloride, chloroform, benzene, carbon disulfide, ethyl ether, and camphor. So these are just ones they selected. There's many more solvents than this. And they've listed their boiling point, what they would normally boil at degrees Celsius. And then this constant, this boiling constant, which is part of this equation. So you don't memorize these. These are something you'd have to look up. So when you do these problems in the homework, you are going to do some of these calculations in the homework. The problem itself does not tell you what the boiling point or the Kb is for that particular solvent. It's going to depend on you looking at this table 11.5, which is in the textbook, or it's here, or it's also the same table you can see in the packet. So this is, we already talked about this equation, right? For, oh, this is important. The way that the questions are usually worded, you're going to see is, let's say you were doing a boiling point calculation. It'd say, okay, you have this water and you dissolve some sugar in it, and it tells you the amounts. What is the boiling point of the sugar water solution? Well, if you go to calculate this, that doesn't tell you the boiling point. That tells you how much it went up. So then you have to, down here, it tells you the change in boiling temperature is added to the normal boiling point of the solvent to get it. So you need this number too here. So if you find out that let's say your change in temperature of boiling came out to 0.5 degrees and it was water, then the new boiling point would be 100.5. If you calculated a change of temperature and boiling of 0.5 and it was for benzene, then your new boiling point would be 80.6. It would go up by however much you calculated, you add it. So freezing point depression, the freezing point is lowered when you have a solution. So a saltwater solution freezes at a lower temperature than just pure water, and a saltwater solution boils at a higher temperature. So when we say water boils at 100 and freezes at 0 Celsius, that's for deionized water. If you have tap water, that has stuff dissolved in it. If you have salt water, it's going to have a higher boiling point and a lower freezing point than 100 degrees and 0 degrees. So we already have this equation, change in temperature and freezing. This is the same table, but now I've circled the normal freezing points of these solvents, and here's their Kf. So Kf, the freezing constant, and the boiling constant are two different numbers. So you have to look up the right one. Now in this case, once you calculate the change in temperature of freezing, since it's called freezing point depression, you would subtract it from the normal freezing point. So water freezes at 0 normally. If you have something dissolved in it and you calculate its delta T of freezing, you would subtract it. So maybe it would freeze at -1 degree Celsius, or for like some of these other ones that are already negative, it would become more negative. So we'll do an example. Okay. I think I'm going to pause now and we're going to actually do that example before we go on. So let me switch over here to a different screen. Okay, so you should see now page 124 of the packet in front of you. And this was, we did these calculations, I did these calculations in the first video. And as a quick review, we had a solution. And it was 15.6 grams of lauryl alcohol, and we decided to call it LA. This is its molar mass, and it has been dissolved in 148 grams of the solvent ethanol, and that was this ethanol's molar mass. In question 1, we calculated the molality of the solution, and that's going to be important because we're going to need the molality to do this next calculation, because we're going to do one of these delta T calculations, and they have molality in them. So keep that in mind, that 0.566 molal. All right, so the last problem down here says, what is the boiling point of the solution? I think I'll zoom in just a little. What is the boiling point of the solution, given that the normal boiling point of pure ethanol is 78.5 degrees Celsius and its boiling constant is 1.22 degrees Celsius per molal? So we need the equation, a real simple equation that says the change in temperature for boiling is going to be the boiling constant times the molality of the solution. And so for this example, the boiling constant is given as 1.22 degrees Celsius per molal. And the molality we calculated in question 1 as 0.566 molal. Cancel those, and we end up with the change in temperature of boiling of 0.691 degrees Celsius. So that tells us our boiling temperature is going to go up by that amount. How do I know up? Because it's called boiling point elevation. So now we say the new boiling point is going to be our original boiling point, 78.5, plus our delta, or that's the change. And so that comes out to 79.2 degrees Celsius. I round to the 10th place because remember when we add this way we count sig, so this was 3 sig figs because I had a 3 sig fig number times a 3 sig fig number, so that's 3 sig figs. When we add, we don't count we count decimal places when we add. So first you add them and then you round. And in that case, rounding to the 10th place got us that. So that's as simple as it is. If we had been asked to calculate the freezing point, which I don't have the normal freezing point in anything in this problem, but if we were doing a freezing point problem, we would subtract over. This would be a subtraction. We would take the normal freezing point, not the boiling point, but the normal freezing point, and subtract the delta that we just calculated, the delta T. Freezing goes down, boiling goes up. Like, let's think of it as stretching. It goes, the freezing point gets lower, the boiling point gets higher, the whole range kind of stretches. So that's all there is to those calculations. Now, they can get a little more complicated. And I've seen ones in their homework where they ask you, they give you some information, and then they ask you to calculate a molar mass. We'll try one of those maybe at the end of the video. I'll pull up the homework problem and we'll do one of those. Okay. So for now, I'm going to switch back to the PowerPoint so we can finish up this part. And let me see here, 1 second. New share. Okay, PowerPoint. Okay, so now we should be back to the PowerPoint again. And so now we're going to look at colligative properties of electrolytes. So electrolytes, remember from good review, going way back to chapter 4, electrolytes are substances that when they're dissolved in water, they form ions. So we have we have strong electrolytes, and those are things like soluble salts, sodium chloride, potassium nitrate, etc. And we also have strong acids. Those are strong electrolytes. Strong bases are strong electrolytes. So what's interesting about this is that these colligative properties depend on the number of particles that are in solution and not what they are. So in the electrolytes, which by definition are breaking into pieces when you put them in solution, they're going to have a greater change than those of non-electrolytes. For example, every sodium chloride breaks into 2 ions. So we have a picture down here of a sodium chloride dissolving. And so every time, what we would call as 1 sodium chloride is going to give us 1 sodium and 1 chloride. Colligative properties don't care that this is a sodium and this is a chloride. It just cares at how many of them there are. So 1 mole of sodium chloride will give you 1 mole of sodium and 1 mole of chloride. So 2 total moles of particles. So 2 ion particles. On the right side, this is a non-electrolyte. This is methanol dissolving in water. It does not break into ions. So 1 mole of methanol just gives you 1 mole of methanol. So this is going to make a difference when we do calculations of, let's say, freezing point or boiling point changes with salt solutions. Okay. All right. So what would that mean? Before we do this slide, let me go back a second. One sec, I lost the screen. Give me 1 second. I hit escape too many times. 1 minute. Okay. There we go. All right. So let's get it right. Sorry about that. So what does that mean? Well, remember that we said that the change, let's say the one we just did, the change in the temperature for boiling is equal to the boiling constant for your solvent, which you look up in the table, or it has to be given to you if it's a quiz or something, times the molality of the solution. So over here in our methanol, let's say we had a solution that was 1 molal. So 1 mole of methanol per kilogram of water. That's the molality. let's say over here we had 1 molal, but it's of sodium chloride. This is of methanol. See if I can write this one. CH3. It's hard to write with this thing. OH, CH3OH, doesn't matter, but that's its formula. Okay, so what are we going to put in here for M? Well, you say, well, 1, because you got 1 molal, 1 molal. Well, for this one, you would put 2. So for sodium chloride, this is equal to 2 molal of particles. And that's what matters here in the equation, how many particles. So 2 molals, we'll just call it total, okay? And that's what matters. The total amount of particles you have in there influences the, because the colligative properties are just about how many particles are there, how many interactions are happening, not what they are, okay? In this one, the molality would just stay 1 because it's just 1 particle. So if we were doing the calculation, switch back to my pointer here. So if we're doing this calculation for this sodium chloride, even though it's 1 mole of sodium chloride per kilogram, we would put a 2 in here because each sodium chloride is 1 sodium and 1 chloride. And for methanol, since it doesn't break up, it would just be a 1. So that's where electrolytes get a little funny. Now, what if we had something that was a little bit different particle, okay? What if we had something like FeCl3? How many ions does that yield? Well, it gives, when that dissolves, it gives 1 iron, which is a +3, and 3 chlorides. Ooh, sorry, let me erase that. Got a little excited there. Doesn't want to erase. There we go. Okay, so it gives 1 iron, but it gives 3 chlorides. So we have 4 total. 1 iron, 3 chlorides. So our total is 4. So our molality, whatever we calculated for, if we calculated our molality based on iron 3 chloride, let's say it came out to 1 molal, we would have really 4 molal of particles. So that's, you got to keep that in mind. Okay, so that's something to keep in mind. Now, for example, if you've ever lived in a cold climate, in the winter time, when the streets start to freeze and they don't want ice on the streets, they sprinkle salt on it. Usually it's a calcium chloride and not necessarily sodium chloride. They could use sodium chloride, but they usually use something like calcium chloride. And that has a lot of particles in it. Calcium chloride would have 3 particles. And so it lowers the freezing point if you get that in the water. So the freezing point of the ice actually gets lowered quite a bit or enough so that it doesn't freeze as easily and the streets stay wet instead of frozen. So that's what the ice is about. I'm sorry, the salt is about on the ice, icing the streets. Okay, now this is going to get a little bit, I'm going to apologize for this in advance because this is confusing. This is something called the Van Hoff factor. But here's the weird part. 1 mole of, we're using sodium chloride as an example, but this would go for any salt. It's not just sodium chloride. 1 mole of sodium chloride in water does not give really 2 moles of ions. So everything I just said is not 100% true. Not absolutely 100%. That's but I said here, it's true. We've been lying to you for 2 semesters. What do I mean by that? Well, we've been telling you from the beginning that when you put sodium chloride into water, it breaks into a sodium over here and a chloride, and they both get surrounded by water and nothing recombines. Well, it doesn't work that way. very little things in nature are really 100% like that. Some of the sodium and chlorides do this. They kind of are still surrounded by water. They're not part of a giant salt particle anymore, but they combine and are both surrounded by water. And this is called an ion pair, okay? So that's what this says. Some sodium and chloride reassociated as hydrated ion pairs. So hydrated means they have water bound to them in their ion dipole. But remember, this positive and negative is pretty attractive. So they're gonna, some of them, if they get close enough, they might stick to each other a bit. So they're not forming a precipitate. They're not forming that big salt crystal, but some of them do that, okay? So the true concentration of particles is going to be somewhat less than 2 times the concentration of sodium chloride. So before I said in the last one, well, if you had 1 mole sodium chloride, it's really 2 mole particles. It's really less than 2, 1.9 something. How much less? It depends on the concentration of the solution. So reassociation into ion pairs is more likely at higher concentration. Makes sense, because the higher, if you have a really dilute solution, then the chance of them bumping into each other and recombining and sticking is a lot less than if you have a really concentrated solution when they are pushed together. So the number of particles present is dependent on your concentration, and that number is called the Van Hoff factor. So let's look at sodium chloride down here. The limiting value is 2. What does that mean? That means like if everything was perfect. If every time you put a mole of sodium chloride in there, you got 2 moles of particles, 1 sodium, 1 chloride, you get a 2. It's not exactly 2 because some of them, a certain percentage of them are floating around as these ion pairs. Now, why do the ion pairs not count? Well, because remember, we're counting particles for these colligative properties. The colligative properties don't care how big the particles are. They don't care what they are. So an ion pair counts as 1 particle. So a sodium ion counts as a particle. A chloride ion counts as a particle. A sodium chloride pair that's floating around like hooked together counts as 1 particle, even though it's bigger. So if they were all completely, no one was combining and making these hydrated ion pairs, you would have a 2, you would have 2 particles. But depending on the molality here, the concentration, the higher concentration, a percentage of them are floating around as these pairs. And so you can see this number goes down as the concentration goes up. Sucrose is here, that's sugar, table sugar. No ions involved. So it doesn't break into pieces when you put it into water. So this thing we're talking about now is only for electrolytes, things that break into ions. So you see its limiting value is 1. What does that mean? If I put 1 mole of sugar in the water, I get 1. It doesn't matter the concentration, it's still a 1 because it doesn't break into pieces. If you look down here at the potassium sulfate, there are 3 particles there, 2 potassiums and 1 sulfate. Remember when we put polyatomic ions into water, they don't break into smaller pieces of sulfur and oxygen. They just stay as sulfate. So we'd have 2 potassium, 1 sulfate. That's a total of 3. That's our limiting value here. But as the concentration, that's sort of like the perfection. Okay, that's the ideal situation. It doesn't really happen. As the concentration goes up, we have more and more of them that are stuck together as pairs. You notice down here, magnesium chloride, compare magnesium sulfate to sodium chloride. They both have a limiting value of 2 because this would be 1 magnesium and 1 sulfate. However, you notice that for the magnesium sulfate, especially as you go to higher concentrations, it's much less than 2 compared to sodium chloride. You think about why that is, that's because the magnesium and the sulfate have a +2 -2 charge, where this is a plus, sodium is +1, chloride's -1. The attraction is much stronger here. Most of this is all about intermolecular forces of solutions. All this stuff is about attraction of positive and negative. A while ago, I said that a big chunk of chemistry is just studying the force of attraction between positive and negative particles, which is called the electrostatic force. And so much is ruled by that. And so you see that happening here too. The bigger the charge, the more attractive the force. So the Van Hoff factor for a 0.1 molal solution of sodium chloride is about almost 1.9. And over here for magnesium sulfate, it's 1.2, even though there's 2 particles in both of them. Okay, so what does that mean? It's not that hard. It's interesting, it's not that hard. We modify the equation for these. So here's our freezing point depression equation. So before we just had the Kf times the molality, and then we put now this Van Hoff factor in there, okay? And that's what this number is. And you got to look it up in a table. You have no way of calculating it. So the Van Hoff factor, you have to find it in a table. It has to be given to you in the problem. It depends on the concentration, et cetera, et cetera. For non-electrolytes, like sucrose, like the lauryl alcohol in the previous problem I did, those are not electrolytes. I is equal to 1, this disappears and we go back to the original equation. So it's not that hard. It's just like, it's basically a correction factor. So the thing you have to remember is that, first of all, 2 things, that there's this Van Hoff factor, and also that for these ionic compounds, we are breaking them into more pieces so they have a higher molality to begin with, okay? All right. Okay, so that's it for the this section of the notes, and that's really the end of it. There is a few more slides in the PowerPoint that I have on osmosis that I'm not going to talk about. We just kind of out of time. If you're going into any kind of biology or medical field, you might want to go look at those. Osmosis, osmotic pressure. It's related to a lot of things like dialysis. It's related to blood cells. It's related, it even is related to reverse osmosis and how they purify water. So you might want to take a look at that, although I'm not going to quiz you on it. So that's it. Thank you.